So things are going to get kind of fun right now. We're going to start dealing with a data set about superheroes and their connections to each other, believe it or not. And as before with the Movie Lens dataset, we're going to start off with some simple examples and work our way up to more interesting problems later in the course. But for now, I just want to introduce the data and how to play around with it. So believe it or not, someone actually went out and looked at every single Marvel comic book and kept track of all the superheroes that appear together within the same comic book. And what we're doing is we're treating those co-appearances within comic books as social connections. So the fact that, for example, the Hulk and Spider-Man appeared in the same comic might imply that they're friends, if you will. So we can build up these complicated graphs where we have these references of who appeared with who in different comic books. So in this example here, maybe the Hulk appeared with Iron Man and the Hulk appeared with Thor, but Thor only appeared with Iron Man. And maybe they were in different comic books, and maybe Spider-Man and the Hulk are connected by appearing in the same comic book, but let's pretend that the Spider-Man and Thor never actually appeared in the same comic book. Totally made up social graph here, but it gives you a very simple example of what a social graph looks like. And just like we can construct something like this in the context of superheroes who appeared with each other in the same comic books, you can also apply this to big social networks like Facebook or what have you. Same idea. Networks of friends look like this, and they can have complicated shapes and structures. So playing with this data can be pretty interesting. But for now, let's do something simple and try to figure out who the most popular superhero is based on this data that we have. Let's take a look at what the data looks like. So there's two files that come with this data set that we're going to work with. One is called marvelgraph.txt, which contains the actual social graph itself in kind of a strange format. And then there's marvelnames.txt, which just maps superhero IDs to their human readable names. Okay? So looking at marvelgraph.txt, every line is just this big stream of numbers. And the way to interpret it is the first number represents a given superhero, and all the subsequent numbers represents all the superheroes that appeared with that superhero in other comic books. So again, the first number is special, that's the hero that we're talking about, and it's followed by a list of all the heroes that appeared with that hero, okay? And to map those hero IDs to names, we can do that with the marvelnames.txt file. So for example, we can see that Spider-Man is 5306, and actually he appears with whoever 4395 is in this example. Spider-Man is pretty popular, but let's find out if he's actually the most popular. So pretty simple, straightforward problem here. Our high-level strategy will just be to parse in that input line, one line at a time. And since we don't really care about the actual individual connections for this problem, we just want to find out who's the most popular. All we care about is the total number of connections for each superhero. So we're going to look at each line of input data, extract the superhero ID, that's the first number there that we're talking about, and then just store the count, the total number of other superheroes that appear with that superhero. Now, remember, these can span multiple lines, so the same superhero ID might be broken up onto two or more different lines, so we need to combine them together somehow. And reduce by key will allow us to add up all the individual lines for a given superhero into one final result. From there, we use the same sorting trick that we've used before. We're just going to flip that around so that the key is the count of how many friends you have, and the value becomes the superhero ID. And then we can just call max on the resulting RDD to find who has the most friends. And friends, again, is a proxy for co-appearances in other comic books in this example. Then we can look up the name of the winner from marvelnames.txt, and display the result. So off to the code. Let's see how that works. Run it and find out who is the most popular Marvel superhero. Alright, so let's get our hands dirty with the Marvel superhero social network data. As before, I have two windows open up here. One is my working folder that I'm using for the course. This is where all of my projects and data for the course are going that I work from. And then I have my download folder where I downloaded the course materials for the entire course. So the two files we care about for data are marvelgraph and marvelnames.txt. If we click on them and preview them, you'll see that they are, as I advertised, marvelgraph again, just a list of lines that have a bunch of numbers on them, where each number represents a superhero ID. The first number is the hero we're talking about, followed by a list of that hero's connections. And then we have marvelnames.txt, which is mapping hero IDs to their human readable names, where the names are enclosed in quotation marks. Okay, so let's go ahead and copy those into our working folder here under C Spark Scala, and fire up the Scala IDE, and we'll import the necessary code to figure out who is the most popular superhero. All right, we'll do our usual dance. Open up the project, open up source, open up the package, right-click on the package, and import from the file system, from where we downloaded the course materials, most popular superhero.scala. And let's open that up and take a peek. Get rid of this other stuff. All right, a little bit more complicated stuff going on here, kind of surprisingly so. A lot of it's because we're dealing with two different data files that have different formats that we have to handle. So let's skip down to the main function where things get interesting, and we'll kind of work back to the other functions here. Usual setup stuff. We're just going to set the log level and create our Spark context. Now we're going to read in the Marvel names.txt file. So the first thing we're going to do is build up an RDD that can map superhero IDs to superhero names. And this is yet another way of doing this sort of a conversion. You know, in other exercises we looked at building up a Scala map object that we just used to do that as we're displaying the end result, and that would work fine here as well. We've also looked at using broadcast variables to load up that map ahead of time and broadcast that to each individual node in our cluster, and that works too. But you can also build up an RDD, and that will automatically be available to every node in your cluster as well. So a third way of dealing with this sort of a problem here, just for illustration purposes. So to do this, we're going to call flatMap on the parse names with the parse names function that we defined above on this names RDD. So names contains, just to refresh what it looks like, Marvel names.txt looks like this. So every row is a number and a space, and then within quotation marks the name of that character, okay? Now, maybe there's some invalid data in here somewhere. Maybe there are some empty names. Maybe there are some blank lines. In fact, I think there are. So we need to deal with all these different edge cases as well. And that's where flatMap comes in. So if there's a possibility of a line that we cannot successfully parse, we want to use something like flatMap so we have the option of returning nothing for a given line because it's not actually going to end up in our RDD. So that's why we're calling flatMap instead of map. And let's take a look at what parse names does. So remember, this is getting called by flatMap on the raw input data. The input is a string of the Marvel names.txt file. And the output is going to be an option, a Scala option, of a tuple of a superhero ID and the superhero name. Now, we haven't talked about options before. Basically, an option is a Scala construct for saying you could have data or you might not have data. In other languages, we have the concept of a null value or a nil value or something of that nature. Scala doesn't have that. Instead, it has the concept of an option that wraps basically a value. And you can have either an actual value returned as an option, and that is a sum value, which is a subclass of option, or you can return a none value, which is also a subclass of option. So by returning an option, you can return a sum, which actually contains data, or a none, which contains no data. And when you're using flatMap, what will happen is that if you return a sum object, it will say, okay, I'm going to actually construct a line in my new RDD based on what's inside that sum object. But if it returns none, it will say, okay, there's nothing actually to do here. I'm not going to create a new line at all in my resulting RDD. Okay, with me so far? Looking at the code makes a little bit more sense, so just take a close look here at what's going on. Now, a little trick here in how I'm going to parse it. Again, if you look at the actual input data itself, what I want to do is extract that superhero ID and the name. And one way I can do that to kind of cheat a little bit is to treat the quotation mark character as the delimiter character. So if I delimit this string and split it up on quotation marks, what do I end up with? Well, this ends up being one field then, the ID followed by a space, and then the name itself, which is between the next two quotation marks, becomes our second field. Okay, so even though it doesn't really look like it's quote delimited data necessarily, by treating that quotation mark as a delimiter, I'm getting pretty close to what I want, and that's what I'm going to do here. So the first thing I'm doing is splitting the string based on a quotation mark, and that gives me back, hopefully, more than one field. So if I actually end up with a successfully parsed line that has an ID and a name, I'm going to have more than one field, and I can continue on. And what I will do is take out that first field value, which is the hero ID followed by a space, called trim to get rid of that space, and then convert that to an integer value. Okay, so that's basically plucking out the superhero ID and converting it to an integer. And then I will take the second field, which is what appears between the second set of quotation marks, and use that as the name. Okay, and that gets wrapped in a sum object, indicating that I did in fact have valid data to return for that line. Now, if I have a blank line or a line that's missing a name or something, or maybe the quotes are all messed up, I'll just return none. In that case, I won't have more than one field, and I'll return a none value, which tells FlatMap, ignore this line, don't do anything with it, there's nothing here to see. Okay. So after this line, we end up with a new names RDD that is just a key value RDD that maps superhero IDs to their names. Might come in handy later, right? All right, let's load up the social graph itself. So the next thing we're going to do is load up the Marvel graph.txt file into a lines RDD, and now we're going to call map on it using this count co-occurrences function. So what we want to get, as we talked about in the slides, is a new RDD that maps hero IDs to how many connections they have. And remember, this can be split up on multiple lines, so we're going to have to reduce that later on. But for now, let's just convert each line of input to a hero ID and how many connections they have. You can see all we're doing here, we're using another regular expression, kind of like we did back in the word count example. But instead of W plus, we're using S plus. That lowercase s plus is a regular expression that means split it up based on white space. Whatever white space is. It might be multiple spaces, it might be tabs and spaces. I don't care. Just split it up on white space, please. And that's what it gives me back. So what I'm going to get back here is a list of strings that represent the superhero ID and all of the superheroes connected to that superhero. But all I care about is that first entry, the hero ID we're talking about, so that's element 0 converted to an integer, followed by the number of connections. So that's just going to be the total length of that list minus 1 to subtract off that first character ID. Okay? With me so far? Hope so. Don't be afraid to go back and rewatch things if you're losing me here, but it's pretty straightforward. All right, so at this point we have a pairings RDD that is key value pairs of hero IDs to numbers of connections. Since these can span multiple lines, we need to do a reduce by key to add them up in that case. So if we have more than one line for the same superhero ID, this reduce by key operation will combine them together by adding them. And that gives us our RDD of total friends by character. So what we have at this point is key value pairs of hero ID to the grand total number of connections that hero has. Now to sort it properly, we're just going to flip it and make the key the number of connections and the value of the hero ID. Now I could just sort that and print out the results, or I could, if there's all I'm really trying to find out is the person who has the most friends, right? So rather than sort it and print everything out, I'm just going to find the maximum value. And if you call max on a key value RDD, it will find the maximum value based on the key. So that's why we had to flip it there. So that will give us back the result of the most popular superhero. All we need to do at that point is call lookup on our names RDD to figure out the name of that person, and we can print it out. And there's where we actually print out the result with string substitution, where we put in the name of the result and the end result of how many co-appearances that hero had. So, wow, a lot of talking, a lot of code to talk about, but let's just run it and get our result. The suspense is killing me. Run configurations. Scala application. Most popular superhero. com.sundogsoftware.spark.most popular superhero. Let's see what happens. And if we should get an answer real quickly, it is... Ta-da! And the winner is Captain America. I wouldn't have guessed that. I would have guessed someone like Spider-Man, but it turns out Captain America gets around. He shows up in a lot of comic books. It's a good guy. He deserves it, right? All right, so that's a simple example of using the Marvel dataset, and we're going to do some more interesting stuff with it next. We're going to figure out degrees of separation and find out who is the Kevin Bacon of the Marvel superhero universe. We'll do that next. So if you want to get your hands on with this code and fiddle with it, as always, I encourage you to do so. Here's an idea. Instead of just printing out the most popular superhero, print out the top 10 most popular, and maybe the top 10 least popular. Give that a try.